This video will be about the Fibonacci sequence, what it is, who invented it, and how it can be seen throughout the world. First, I'll start by giving the definition of the Fibonacci sequence. As the name suggests, it's a sequence, which is an ordered collection of numbers. For this sequence, the next term is the addition of the previous two terms. For example, we start at 0 and 1. 0 plus 1 is equal to 1. 1 plus 1 is equal to 2, 1 plus 2 is 3, and so on and so forth for this never-ending sequence. In a more mathematical sense, f, which denotes the name of the sequence, of n is equal to f of n minus 1 plus f of n minus 2. You should notice that knowing a certain term in the sequence requires knowledge of previous terms, which may not be known at the time. In this way, it's what is called a recursive function, where you have to apply the rule again, but this time to the previous terms to get the previous terms before them. In other words, f of n minus 1 is equal to f of n minus 2 plus f of n minus 3. This might be confusing to understand when seeing it for the first time, so an example is given at the bottom. You want to find the third term, which is the addition of the second term and the first. At this moment, the second term is unknown, so you reapply the definition to the second term, which is equal to the first term and the 0th term. We know, given by the problem, that the 0th term is 0 and the first term is 1. So the second term must be 0 plus 1, which is 1. Now that we know what the second term is, we know what the third one is, since that's just the second plus the first. So applying the rule again, we get 1 plus 1 is equal to 2. There is confusion on what number the sequence starts at, whether it starts at 0 or 1. The truth is, you can start at any arbitrary number that suits your needs. There's really no right answer to this, and instead, the different starts are considered different styles. There's advantages and disadvantages to both, and it honestly depends on what you need the series for and what type of problem you're trying to solve. However, I will note that the creator of this series, who will be introduced shortly, started the series at 1, yet many say that he simply omitted the first term, so it's honestly unclear. When did it start? Who invented this series? Leonardo of Pisa in 1175 AD, otherwise known as Fibonacci, was the first to recognize this sequence. He was born in Italy, educated in North Africa, and is a very sophisticated mathematician during his time. The sequence was not his only contribution to mathematics, and listing all his works in history would take another presentation. The most important of his other contributions is the fact he also invented our current numbering system, the one with 10 digits, 0 to 9, with decimals, yes, that one. This is the system that replaced Roman numerals and is used today. We're not focusing on that, but it's always good to note the other contributions an important man may have made. So, honestly, it's a list of numbers. What's so special? We see a ton of lists of numbers in everyday life anyways, like even on our shopping list, that kind of stuff. What gives? Well, first I'll talk about the population prediction to give an introduction what type of problems the Fibonacci sequence solves. More importantly though, the sequence holds the golden ratio. I'll go over each topic. Fibonacci first found the sequence by doing a thought experiment. If he had immortal rabbits, as you do, where the female will always produce a pair of rabbits, one male, one female, and each month the female produces new rabbits, with just born rabbits having to wait a month before producing another pair. How many pairs will occur after 12 months? At the end of the first month, there will still only be one pair. There is one male and one female, so one pair. At the end of the second month, the female produces a male and female, so now there are 2 males and 2 females. At the end of the third month, the female again produces another rabbit. So there are 3 pairs. By the end of the 4th, 2 female rabbits produce 2 new pairs, so now there are 5. By the end of the year, there will be 144 rabbits. So I hope the connection is simple to make, that this rabbit problem essentially draws the Fibonacci sequence. Now, this is also related to real life if you wanted to draw the family tree of a male drone bee, since they only have 1 parent. These aren't the only problems out there where the Fibonacci sequence appears as the answer, and there are many more than simply 2 examples. Actually, the sequence appears quite often in nature, which I will go over for the rest of the presentation by introducing the golden ratio. Seems like quite a random number, 1.61803 and so on, but it's a very special number hidden in the Fibonacci sequence. If you take the ratio of any 2 consecutive numbers in the sequence, it will be an approximate of this golden ratio number. As you take the ratio of numbers deeper in the sequence, the ratio will approach the golden ratio itself. On screen, this is shown in mathematical terms. The limit as n goes to infinity of f of n plus 1 over f of n is equal to, the symbol is phi, which is the symbol for the golden ratio. That may look a bit scary, but this mathematical term is repeating what I originally said. As the term you choose grows larger, its ratio closer approximates the golden ratio. As you can see, starting with the first few terms already gives us a close approximation. 5 divided by 3 is 1.6, which is fairly close to 1.61803. There are some neat properties about this number. One of the properties is that the reciprocal of the golden ratio is exactly equal to the golden ratio plus 1. In another term, the reciprocal of a number is equal to that number plus 1, and it's the only number that does this. Not only that, but the square of the golden ratio is the same as the golden ratio plus 1. As you can see on screen, there's also a very interesting fraction that the golden ratio makes. It's 1 plus 1 over 1 plus 1 over 1 plus, and so on and so forth. There is also a geometric representation. If you have a line of length 1, there is a single point on that line where the ratio of A to B, which you see labeled on screen, should be the same as the ratio of B to C. The point to cut is the golden ratio minus 1. There's also some more geometric representations of this idea on the right. There's a visualization of the golden ratio which may be more familiar. Start with the first 2 Fibonacci numbers, 2 squares with length 1, which you can sort of see very small in the center there on screen. Then add the lengths of the squares and create a new square with length 2 alongside the original. Then add the length of the previous 2 squares made, which will be of length 5, and draw a new square. Keep going with this method, and then draw a half circle from corner to corner of the square. This is the golden spiral, which is also known as the Fibonacci spiral. It's important as the spiral is seen throughout the world, from science to art to photography to technology. It's simply everywhere, and I'll give you some examples. This is one of the ways the golden ratio shows up in science, through nature. Sunflower seeds need to be packed tightly as possible, and in that way they will have a slight curve when they're packed together. And if you curve it too far, well, then they just won't be packed. They'll be sort of intersecting each other. It doesn't necessarily work that way. This curve is the golden ratio, and counting the seeds from one direction to another yields the Fibonacci sequence. Shell spirals also follow the golden ratio. It's said that they do this for buoyancy. The golden ratio also appears in chemistry, where, well, truth be told, this is a challenging subject having to do with quantum mechanics. The important thing of note is that the golden ratio appears in a hydrogen atom when taking ratios of an orbiting electron. It's no secret the golden ratio is utilized in art to create aesthetic pictures, structure, and design. Leonardo da Vinci may have known this best when he created art for Pasolini's book, I apologize on the pronunciation, The Divine Proportion. This book specifically states exactly how the golden ratio can be used to create beautiful works. The picture on the right is the Mona Lisa with the Fibonacci spiral overlaid. Note how her head is perfectly inside the spiral and her arms follow the curve. The golden ratio is also utilized in photography. Common known rule for photography is the rule of thirds, where the screen is literally split up into thirds horizontally and vertically. However, it has a cousin, the phi grid, which is a grid based off the golden ratio, and it's said to create even better composition than the rule of thirds. Another way that the golden ratio is used in photography is to simply overlay the Fibonacci spiral over the picture, and it's said when the picture follows the spiral, it creates better composition and more aesthetically pleasing pictures. The golden ratio also appears in psychology. The human face appears more beautiful, aesthetically pleasing, when the proportions of the face closely match the golden ratio. Almost any part of the human face can be connected to the golden ratio. And for example, you can use the golden ratio on our eyes, our nose, our teeth. For my last example, I will note that the golden ratio also appears in business. On screen, there's examples of how Google uses the golden ratio to create an appealing product. These images may be hard to understand at first. On the right and left, there's a line, and it's cut at that point talked about earlier, where the ratio of the lines is equal to the golden ratio. And they did this from bottom to top and top to bottom. From top to bottom, notice how the letters seem to stop at the points of the golden ratio for each example shown on screen. Google isn't the only company to utilize the golden ratio to create an appealing logo or an appealing product. There's sources out there which say Apple did similar with their logo and their phones, and there's other examples of businesses using this golden ratio to create structure and design. On screen, you will see the references I have used in order to create this video. I will post these links in the description, and I want to thank each source for essentially just giving information about this Fibonacci sequence.